Hello. In this video, we'll explain the problem of estimation with constraints. And to do so, I will start with the general problem of estimation that we have been discussing in other videos. According to it, the goal of the estimation problem is the design of a system that we will usually call the estimator, which given any input variable x that we use to call the observation, produces an output S hat, which is expected to be similar to S. And using the Bayesian formulation, we will assume that we have a statistical model relating S and X. That could be the joint distribution of S and X or any related distribution like the posterior distribution. And we have a dissimilarity metric to measure the discrepancy between S and S hat, which is the cost function. C of S hat. Okay. Well, according to the Bayesian formulation, the design of the estimator will be done with the goal of minimizing the expected value of the cost that we used to call the risk. Okay? So the goal in the minimization, in the Bayesian risk minimization problem, is to minimize the expected value of the cost that we call the risk. Okay? And the general solution to this problem is the minimum risk estimator given by S hat equal to the value of S hat minimizing the expected value of C given the observation. Okay? So keep this in mind. The goal is to minimize the risk, and the general solution is the estimator minimizing this expression, or this is the conditional risk. Okay. We have also analyzed some particular cases. Today we will focus in one of them, which is the square error. In this case, the cost is given by the square difference between S and S square. And we have seen that in this case, the solution is given by an estimator that we usually write in this form, which is the conditional mean. Okay. So we have a general formulation for the problem, and in the particular case of the square error, we have a particular form of the solution. Okay, this is usually called the unconstrained minimization problem because we are not imposing any constraint on the estimator. Okay, and this has some disadvantages because, well, although in many cases we can compute the minimum risk estimator, in many others the computation of these estimates is computationally is intractable. Okay, and well, we can see this just by expanding this. The expected value, the conditional mean, is just the integral of S times the P of S given X, the posterior distribution. And this integral may have no analytical solution in general. Okay, and also we may have the situation where uh, we cannot compute the posterior distribution. Okay, despite the simplicity of the relation between the posterior distribution and the joint distributions, there are many situations where we are given a joint probability distribution of S and X, and we have to compute the posterior. To do so, we have to compute the denominator, the marginal distribution. The marginal distribution is the integral of the joint distribution. This is the usual way to compute it, but there are many situations where this integral cannot be computed analytically. So we have no analytical form for the marginal, so we have no analytical form for the posterior, so we cannot compute the posterior mean at least easily or exactly. Okay. So for this reason, well, there are many approximation methods to try to overcome this, but in this case, we will explore an alternative, which is to impose to the estimator the constraint to be simple. Okay, so we will try to find the minimum risk estimator, but imposing to the estimator the constraint that it should be computationally tractable. Okay. And we will do it by stating a parametric form for the estimator. Okay, so we will use a parameter vector W, and we will assume that our estimator has some known parametric form. Okay, so we will assume that we know that the estimator is a function of the observation that depends on the parameter W. We know the form of this function, but we don't know the value of the parameter W. So we will need to find some way to compute W. Okay, let us see some examples. Just as an example of this, we will show some particular cases. Parametric estimators. And for instance, one used very often is the linear estimator. In the simplest case, in the one-dimensional case, this estimator is given by if W of x equal to Wx. That is, the estimator is just proportional to the observation. Okay? And in the multidimensional case, in the n-dimensional case, Fw of x could be W transpose x. That is a linear combination of the observations. Okay? This is the linear case. Okay? We can also have polynomial estimators. In the one-dimensional case, a polynomial estimator uses a function of the observation, which is a polynomial, with a given degree. For instance, for degree n, it would have this form. Okay? And also we can construct a multidimensional estimators in polynomial form. For instance, for the two-dimensional case, Fw of x could be written as W transpose Z, where W is the vector of these coefficients, and Z is just a vector containing all monomials used to construct the polynomial. For instance, in 2 dimensions, this could be a vector with components 1, x0, x1, x0 square, x1 square, x0, x1. Okay, for instance, this could be the vector set that we could use to construct a polynomial, a two-dimensional polynomial with degree 2. We can increase the degree, adding here more terms with higher degrees, and even we can consider polynomials for the multidimensional case using the same strategy. Fw of x could be W transpose set, and set could be a vector containing, well, all monomials that we could need. X0 square, xn square, and so on. Okay, so well, and these are just an examples. We can use here any arbitrary transformation, or we can use other parametric forms. So no matter what is the form of the parametric estimator, we will assume that we know this form. Okay, so we will say, for instance, we can assume that the estimator is linear, so we can assume that our estimator should have this form. Okay, so the form of the estimator will be given, but the value of the parameter is unknown. So the value of the parameter vector is the degree of freedom which that we have to select the estimator in order to minimize the risk. Okay, so our goal will be to find the parameter vector. So we can rewrite the estimation problem for estimation with constraints as the problem of minimizing the risk, that is the expected value of the cost, but subject to s hat equal to fw of x for some w. Okay, and this is the general form of the general formulation of the problem of estimation with constraints. Okay, and what is the solution? Well, basically, the general solution will be given by the vector of parameters that we will call W star that minimize with respect to W the expected value of C of S f W of X. Okay. And this is the very general form of the solution that which states a minimization problem that we will have to solve in every particular case. So in general, we will be given a cost and we will be given a parametric form and a model relating S and X, and with this information we have to try to expand or compute an analytical expression for this expectation, and after that try to minimize it with respect to W. So we will analyze, we will try to solve this problem in a particular case. We will focus now the attention in a situation where we have a particular cost and a particular parametric form. Okay, so let's assume that we use the cost as the square error and the function as a linear function of the observation. So this is usually called the linear minimum MS estimation. Okay, so we will assume that that estimator, that is the function of the observation, is W transpose Z. Okay? And the cost is the square error. Okay. Note that I write here Z in some cases, in the linear estimation case, Z will be equal to X. So Z is just the observation, but I prefer to write Z just to consider also include in the analysis also these cases. Okay? Z can be a vector containing polynomial terms or any nonlinear transformation. So using Z instead of X, we can find a more general solution. We still call it linear estimation because the important matter here is that this function is linear on W. Okay? This function, as a function of W, is a linear function. Okay, so despite Z can be a nonlinear function of X, so the estimator is a nonlinear estimator of the observation, it is a linear function of the parameter vector. Okay, so using these assumptions, we will try to solve the constrained minimization problem. We have seen the optimal solution is that W star equal to the value of W minimizing the expected value of the cost so we will particularize for this case. We will call this RW. So first of all, we will expand the risk for this case. So the risk will be the expected value of the cost, which is the square error, S minus the estimation, which will be W transpose Z to the square. Okay. And Z is equal to the observation, or it will be a nonlinear transformation of the observation. Since X is a random variable, Z will be a random variable too. So we have to write it in capital letters. Okay. So let's expand this. This is equal to the expected value of a square minus 2 times W transpose expected value of S Z plus the expected value of W transpose Z to the square. Okay, and oops, sorry, we can go a bit more. This is the expected value of the square. The second term is just the expected value of S Z transpose W plus, and we can write this as, well, basically note here that we can write this as W transpose Z to times Z transpose W. So this is W transpose Z, Z transpose W. Okay. So taking the expectation of this, we get W transpose, expected value of Z, Z transpose W. Okay. So we can see here that this is a polynomial in W. Okay? This is a second degree polynomial as a function of W. So, well, we can just plot it in a b-dimensional case, assuming that W has only 2 dimensions. This is like an hyperparaboloid in 2 dimensions. Okay? If this is W0, W1, and this is RW, the risk is is like a paraboloid, uh, a polynomial with degree 2. Okay? And well, this is interesting because any polynomial with degree 2 has only one minimum which can be computed. Well, in general, it has only one minimum, unless for the general cases, but in general, it has only one minimum and it can be computed by differentiation. So we can find the vector W minimizing the risk just by computing the derivative of this function and making it equal to 0. Okay, so we will do it, but before that I will give some names. This here, expected value of Z transpose, is a matrix. Z is a column vector. Z transpose is a row vector, so the product is a matrix. The expectation of a matrix is a matrix, so this is a matrix that is actually the correlation matrix of the random variable set, and we'll write it as R set. And this is a vector because S is a scalar and Z is a vector. So the expected value of S Z transpose is a vector that we will call R S Z. It's the cross correlation between Z and S. Okay. Therefore, the risk is equal to the expected value of the square minus 2 times R S Z transpose. Well, this is the transpose W, plus W transpose RZ W. Okay. And now we can compute the derivatives. And to compute the derivatives, we can apply to well-known differentiation rules for the multidimensional case. In general, the gradient of a linear combination of W with respect to W is equal to the vector multiplying W, and the gradient of a quadratic form W transpose any matrix transpose W is 2 times the matrix times W. Okay, so if we compute the gradient of RW with respect to W, this will be the gradient of this. This doesn't depend on W, it's a constant, so the gradient is 0, we can ignore it. And the gradient of this scalar product applying this rule here will be minus 2 times RSZ transpose plus, and the gradient of this function here will be, I'm sorry, this is no transpose here, and the gradient of the quadratic form will be 2 times R set times W. Okay, and for the optimal parameter, this should be equal to 0, and then W star must be equal to R set to the minus 1 R S set, which is to which is the solution. Okay, this is the parameters of the minimum linear minimum mean square error estimate. And thus, the estimator will be given by a star equal to W star set. Okay? So in general, it will be given by, with a transpose here, R S set transpose R set to the minus 1 transpose set. Well, I should use here the transpose of this matrix, but this matrix in this case is a positive definite matrix, and it can be shown that it's symmetric, so we don't need to compute the transpose. Okay? And that's it.